Good morning, everyone. So today we'll be presenting about game theory, Centipede game. So together with me along is Aifa, Amau, Yonghong, Kapen, Nisha, and me myself, Rongwei, Wan Yi, and Su Qin. So Centipede game is an extensive form in game theory in which formed by two players take turn in choosing the payoff whether to take or pass the payoff. Two players alternately get a chance to take larger share of a slowly increasing payoff. The centipede game conflicts between self-interest and mutual benefit, which people have to grapple. The reason why it is called centipede game is because its original version consisted of 100 move sequences. Just like the diagram shown beside, it's just like a centipede. I'll pass to my friend to talk more about centipede game.
In this centipede game, two players alternately get a chance to take a larger share of an increasing pot of money or to pass the pot to the other player. The payoffs are arranged so that if the pot is passed to one's opponent and the opponent takes the pot on the next round, one receives slightly less than if one had taken the pot on this round. The game concludes as soon as a player takes the stash, with that player getting the larger portion and the other player getting the smaller portion. This centipede game is also a type of subgame perfect Nash equilibrium, or for short we call it SPNE.
SPNE is a refinement of Nash equilibrium used in dynamic games. The strategy profile it is represent a Nash equilibrium of every subgame of the original games with connection between the extensive games and normal formal games. Every finite extensive game with perfect recall has a subgame, and the common theory to determine the SPNE is using backward induction. The SPNE is normally deduced by backward induction from the various ultimate outcomes of the game, eliminating branches which would involve any player making a move that is not credible from the node. Uh, this is example of the extensive game.
This game is also one of reasoning backward in time from the end of a problem and to solve finite extensive form and sequential games. However, results inferred from backward inductions often fail to predict actual human play. Experimental studies have shown that rational behavior is seldom exhibited in real life. Irrational players may actually end up obtaining higher payouts. The Nash equivalent of this game, when no player considering an opponent's choice, suggests that the first player would take the pot on the very first round of the game. But in reality, relatively few players do so. So as a result, via analysis.
So this is an example of centipede game which involves two players, Jack and Jill. And in the diagram 1, the pass and T denotes the take. So the game start with a total $2 payoff. Then Jack goes first and he has to decide either he needs to choose pass or take. But payoff and Jill will get $0 payoff. If he pass, then the total payoff will increase. By 10, if Jill choose to take, then Jill will get $3 and Jack will get $1. But if Jill decide to pass, then there will be an increment in the total payoff. And this goes on until 100 rounds. And at the last round, we can see when Jill choose to take, the payoff will be $101 for Jill and $99 for Jack. But if they cooperate and Jill decide to pass, they will have an equal amount of payoff, which is $100 for Jack and Jill. Now let me pass to the next.
So for this specific example, we actually have 100 subgames, where the first subgame is starting at the player 2's decision node, and the second subgame is starting from the player 1's last decision node, and so on. And the third subgame is at the player 2's second last decision node, and so on. So it keeps on going until it reaches 100 subgames. So as we can see that we are counting the subgames from backward in a backward motion, means it's from behind to the front. So is it a coincidence? No. It is because to solve a subgame perfect Nash equilibrium, we will have to use the method of backward induction, which will be further taught in our slides by my groupmate Wan-Hee. Thank you.
Now we solve the centipede game using backward induction. We will look at the optimal action of each player in each subgame. Now we start from the first subgame. In this subgame, player 2 will get a payoff of 100 if player 2 choose to pass, and 101 if player 2 choose to take. So clearly, player 2 will choose to take because 101 is greater than 100. So now we can delete the subgame and move the player 2 optimal strategy up, and we continue with the second subgame. Now we do the same for player 1. The payoff for player 1 is greater than when player 1 choose to take is greater than when player 1 choose to pass. So player 1 will choose to take with a payoff of 100. And now we delete this subgame again, and now let us move to the third subgame. So now player 2 have the payoff of 99 when player 2 choose to take, and 98 when player 2 choose to pass. So now player 2 will choose to take again. We will do the same for the remaining subgame. And we will eventually get here, and clearly player 1 will choose to take because 2 is greater than 1. So the subgame perfect Nash equilibrium for the game is player 1 will choose to take at first and get a payoff of 2, while player 2 will get a payoff of 0. Now I pass to my teammate.
For the discussion, in real life, instead of taking in the first step, we might observe different outcomes. This means that in real life, one may actually end up in the second subgame or third subgame. They may choose to take a different step. This is simply because not everyone is perfectly rational in real situation of wanting to achieve mutual benefit rather than self-interest, which is an important assumption that we need to arrive at the solution of taking in the first step. But subgame perfect Nash equilibrium has solved for the optimal decision at each step. So even if we end up at different subgame, so we can just follow the optimal decision that made by the subgame perfect Nash equilibrium. So that's all from our group. Thank you.